Hi, I am Jero, and I'll be presenting work done with Stephen James and Benjamin Rossman at the University of Witwatersrand in South Africa. So we are interested in the lifelong setting where an agent is constantly receiving tasks and needs to leverage learned skills to efficiently solve new tasks. In particular, the question we are interested in is, given a new task, can we determine if it is expressible in terms of learned ones? And if it is, can it be solved without further learning? We begin by formalizing the logical composition of tasks in a Boolean algebra structure. So we define the union, intersection, and negation of tasks by composing their rewards. One useful thing this gives us is the notion of base tasks, which is a minimal set of tasks that can be used to specify all other tasks. In general, the number of base tasks is logarithmic and in the number of calls and can be used to specify an exponential number of total tasks. Another useful thing is, given a new task, we can obtain a Boolean expression for it by using the sum of products method. So we can obtain the Boolean expression for a given task, but can we solve it without further learning? Well, we first note that learning normal value functions is not sufficient, since in general, combining them doesn't give anything useful. So we introduce extended value functions, which are simply goal-oriented value functions, but defined for a single task. This is done by extending the task reward function such that it penalizes the agent for reaching goals different from the ones it wanted to reach. It encourages the agent to learn about multiple goals, not just the nearest or most rewarded one. So we generally get nothing useful by combining normal value functions, but with extended value functions, we can provably get optimal results. In particular, we can optimally solve the union, intersection, and negation of tasks by doing these simple operations over their extended value functions. For example, after learning the left and top tasks in the forums domain, we can solve their union, intersection, and even more complex compositions like exclusive OR. So this gives us all we need to leverage zero-shot composition for lifelong learning. Say we have learned two tasks, M0 and M1, and we are given a new task M. We can simply use the sum of products to determine a candidate Boolean expression for it. If that Boolean expression evaluates to the given task, then we can solve it without further learning by similarly composing the extended value functions. If not, then we can learn it and add it to our library. We demonstrate this in the forums domain. The dots here show the various goals, and there is 40 of them, giving about 1 trillion possible tasks. We test our approach with 3 task distributions. First is desampled, where the task goals are sampled uniformly at random. Next is the best distribution, where the first 6 tasks are the base tasks. So the agent only needs to learn these 6 tasks and can then solve any other task zero-shot. Finally, the worst distribution, where the first 40 tasks are defined by each goal. So the agent is forced to learn and store the maximum number of tasks, since none of them can be expressed as a logical combination of the others. These are the results. The black curve here is for the distribution where the agent receives tasks uniformly sampled at random. We see that the agent only needs to learn and store a few tasks and can then solve all other tasks using zero-shot composition. Notice how even the worst-case task distribution outperforms max cure. And max cure here is cure learning with optimistic initialization that maximizes over the learn cure functions. In summary, we can leverage zero-shot logical composition to quickly generalize over a task space. In fact, we have a logarithmic upper bound on the number of tasks that need to be learned and stored. We believe this is a step towards both interpretable and simple, efficient lifelong learning.